for wind speed. What happened? Sorry, so I have something bizarre. So I repeat, this slide shows the surface elevation of wind waves recorded at a probe located at a fetch of 2 meters for a wind velocity of 9.5 meters per second. The experiment were conducted in the large air-sea interaction facility in Marseille, Lumini. You can observe the modulation of the free surface of the water wave. It is a similar experiment here. It is a wind wave generated in Lacif, but the probe is located at a larger fetch, 18 meters. But you can observe also the modulation of the free surface. So now in the open field, we observe the same trend. In fact, modulation still are present. The fetch is 80 kilometers and the wind speed is 7 meters per second. So modulation of amplitude and frequency is an inherent feature of the surface ocean wave. So what is the physical mechanism which produces this modulation? In fact, it is due to the resonant four-wave interaction which occur among the waves located in the group. So today I will use a nonlinear Schrödinger equation to investigate these problems, that is the effect of the vorticity on the modulational instability of surface wave. It is an elegant analytical method to deal with this problem. So the nonlinear Schrödinger equation is an equation which governs the spatio-temporal evolution of a complex amplitude of weakly nonlinear dispersive waves. So when the wind blows at the surface of the sea, the effect is twofold. It generates waves and it amplifies these waves, but also it generates a shear in the water, that is vorticity. In coastal zones, the combined effect of current and bottom friction also can generate a shear flows in the water and so vorticity. So we can claim that generally ocean waves propagate in the presence of vorticity. So it is difficult maybe to ignore this presence of vorticity. So the studies on modulational instability, which is in fact the Benjamin Ferrier stability, in the presence of vorticity are not so many. The first list corresponds to the studies, to the paper within the framework of the NLS equation. So in blue, so today I will present 2 parts. The first part concerns, in fact, gravity waves in the presence of vorticity. I presented already this paper, this result in a conference in Toronto. Maybe you remember, of this conference. And in the second part, I will present a work I have done in collaboration with Malek Abid, Hongshu Su, and Yanin Chen on the effect of vorticity on gravity capillary waves, on the modulation of gravity capillary waves. There are also a work using a fully nonlinear water waves equation, but today I will focus my talk on modulational instability by using the NLS equation. So this is the geometrical configuration of the problem. So on the left, we are working in the fixed frame of reference, and on the right, we are working in a frame of reference moving with with the velocity at the free surface, with the current velocity at the free surface. And due to the Galilean invariance, we can use indifferently the two frame of reference. But I will work with the second frame of reference because I am mainly interested in the effect of the shear, that is the gradient of the underlying current. So when omega here represents the shear, that is the intensity of the shear current. So when omega is positive, it is this case here, the waves propagate downstream. And when omega is negative, it is this case, the wave propagate upstream. So eta is the surface elevation, h is the depth, c represents the phase velocity of the wave, x is the longitudinal coordinate, and z is the vertical coordinate. So I will consider only positive value of the phase velocity of the wave, but omega, that is the shear, can be positive or negative. So I will mention here in red that the vorticity is opposite of the shear. It is minus omega, but I will use differently omega to talk about shear or vorticity. So I assume that motion induced by the waves is potential because the Kelvin-Lagrange theorem states that the vorticity is conserved when you consider a fluid which is inviscid and incompressible, and when the forces derive from potential. And in order to have the shear constant, we must assume that the waves are potential. So phi here represents the velocity potential due to the water wave. So the system of equation we have to solve is the following. So we have the Laplace equation in all the domain and the three boundary conditions. The bottom boundary condition, the vertical velocity vanishes. The kinematic boundary condition of the free surface here is equation 3, and equation 4 is a dynamic boundary condition at the free surface. So we have new term due to the presence of the vorticity. So the system of equation is invariant following the following transformation. So in fact, we can restrict our study to wave with positive phase velocity, but we have to consider positive or negative value of the shear. So in order to eliminate the stream function, so maybe I forgot to comment something. So there is a psi here is a stream function, and j is acceleration due to gravity. So I repeat, eta is the surface elevation and phi the potential. So in order to eliminate the stream function, so we derive the dynamic boundary condition with respect to x, and we use a Cauchy-Riemann condition, and we get this equation, which is a new version of the dynamic boundary condition, but we have only as dependent variable the surface elevation eta and the velocity potential phi. So we will use the multiple scale method to third order. This we apply so the multiple scale method to this system, to the previous system of equation to third order. So we will consider only weakly nonlinear wave train which propagate on a uniform shear current of constant intensity omega. So here epsilon is a small parameter, xi is a slow variable, the spatial slow variable, and tau also is a slow time variable. X and t are the fast variable, But here I am only interested in the slow variable that is on the envelope of the water wave. K and omega are the wave number and the frequency of the carrier wave, and A is the complex amplitude, that is envelope, which depend only on the slow variable. So we inject this expression. We have the same for the potential, and we, after Tedus calculation, we obtain this NLS equation given here with capital L, which correspond to the dispersive coefficient, and capital N correspond to the nonlinear coefficient. So we have derived explicitly the expression of these two coefficients. So in order to simplify this expression, we introduce some parameter, mu, which is a dispersive parameter. In fact, it is a normalized depth by the inverse of the wave number of the carrier wave. Sigma is the hyperbolic tangent of the dispersive parameter, or rho is equal to the ratio of the group velocity to the phase velocity of the carrier wave. Omega bar is a normalized shear. The normalization is the frequency of the carrier wave. Small omega is the frequency of the carrier wave. X also is another normalization. It is sigma omega bar. And here we have the analytical expression of this coefficient. Note that there is no singularity here because X is strictly greater than -1. When X goes to -1, the shear goes to -infinity. So omega is the frequency of the carrier wave as a function of the shear. When the shear is cancelled, we find the classical expression for the frequency, for the phase velocity here, and for the group velocity of the carrier wave. So there is an important things here. I rewrite the NLS equation, so you have the dispersive coefficient there. And here you have two parts which correspond to the nonlinear coefficient. So this term here in red is the mean flow due to the modulation. And this third line corresponds to an interaction, nonlinear interaction between the vorticity, which occur in the term H omega bar, here and here. And there is a nonlinear coupling between the mean flow and the vorticity. And it is very important, in fact, for the properties of the modulational instability of water waves. Generally, this mean flow goes to 0 when H goes to infinity. So you have something going to 0 multiplied by something going to infinity. But now we have to, compute the limit of this product, of the vorticity with the mean flow. So the general expression of the mean flow is given here. And the mean flow presents this limit when H becomes very large. And as you can see, the mean flow evolves when H is large, like H power -1. And so the product, in fact, has a finite limit when H goes to plus infinity. Finally, in infinite depth, the NLS equation can be rewrite like that. And there is a new term here, which is due to this nonlinear interaction between the mean flow due to the modulation and the vorticity and the shear, which disappear. In fact, this term disappears when the shear disappears. So maybe I forgot to mention that capital A is a complex envelope of the velocity potential. So now I come back to to the NLS equation in infinite depths for the complex envelope of the surface elevation, which is given here. But I rewrite this equation in another form for the nonlinear coefficient. And it is important to show when the shear, the normalized shear, will cross the value minus 2/3, the nature of the NLS equation will change. So when the shear is larger than minus 2/3, the NLS equation is self-focusing, and we can have modulational instability. But when the normalized shear is less than minus 2/3, when it satisfies these inequalities, the NLS equation is defocusing, and there is no Benjamin-Feller instability. So it is well known that the NLS equation admits the Stokes wave solution. In fact, it is the envelope of the Stokes wave solution, where A0 here is the amplitude of the Stokes wave, and A is the envelope, the complex envelope of this uniform Stokes wave train. So we consider a linear stability analysis. So we perturb with infinitesimal perturbation the amplitude and the phase. So delta is very small against 1, and delta omega is very small against these terms. So we inject this expression in the NLS equation, and we linearize, and we arrive to a system of two linear differential equations with constant coefficient for delta A and delta omega. And we know that the expression of delta A and delta omega are given by the right hand side of this equation, where L is a wave number of the perturbation, and lambda corresponds to the complex frequency. So the imaginary part will give the rate of growth of instability, and the real part will give the frequency of the perturbation. So the condition of instability with respect to the side bounds, it is too small perturbation, is given by this inequality. That is, that the product of the dispersive coefficient and the nonlinear coefficient must be positive. So L tilde and N tilde are normalized coefficient, and we can get the expression for the gross rate of instability, which is given by this expression, which is a function of the wave number of the perturbation, of the instability, and also of the frequency and wave number of the carrier waves, and also of the coefficient, the nonlinear and dispersive coefficients. We can compute also the maximal rate of growth, which is proportional to the square of the wave steepness of the carrier wave. And we have also the corresponding wave number. So the wave number L of unstable modulational instability must satisfy these inequalities given here. So if I normalized the wave number of the instability by the wave number of the carrier wave, in fact, we can see that the bandwidth of instability is proportional to the wave steepness of the carrier wave. We have obtained an interesting result, in fact, a complete restabilization when the shear is less than this value given here. In terms of the normalized shear, it is when X is less than minus 2/3. So we have, and this occurs whatever the depth. It's a complete restabilization, whatever the depth. So this figure represents the stability diagram in the plan of vorticity, that is X. And here it is the dispersive coefficient, that is the normalized depth. And you can see when X is between -1 and -2/3, we have a complete restabilization, whatever the depth. And it is important also to see that the critical value of the dispersive parameter, which is 1.363, is unchanged in the presence of vorticity. So in order to test our computation, our calculation, we have performed some numerical simulation. It is an infinite depth case. The wave steepness of the carrier is 1/16. The wave number of the carrier waves is 8. The wave number of the instability, there is one mode of instability, in fact, in the computational spectral domain, which is egal 1. So we have a group of 8 waves. So we start, in fact, at 200 period, we introduce a ramp where at 200 period, the vorticity is 0. And at 600 period, the vorticity is minus 0.83. And it is a slow variation. So on 400 period, between 0 and 0.83, not that minus 0.83 is less than minus 2/3. So we have the evolution, the normalized evolution of the envelope. So we have the famous Fermi-Pasta-Ulam recurrence. So we have a modulation, a series of modulation, demodulation, when there is no vorticity here. But when we introduce a vorticity, we can see that you have a complete restabilization because this value of the vorticity corresponds to complete restabilization. So I present some result on the rate of growth, the normalized rate of growth by its value when there is no vorticity. So all the curve will pass through this point 0, 0, 1. So this curve corresponds, the dash dotted line corresponds to the case of infinite depth. And you see that as the shear increases, the rate of growth increases too. But in finite depth, it is these two, the solid line correspond to finite depth, kh equal 1.40, and the dashed line correspond to kh 1.60. So we have an increase, but after we can have also a decrease in restabilization. So here also it is the rate of growth as a function of the normalized wave number of the unstable perturbation for infinite depth, where the dispersive parameter is 2. And when we increase the shear from minus 0.5, we observe also an increase of the maximal rate of growth, but also an increase of the bandwidth of instability. The same trend also in infinite depth. We observe also this increases of the maximal rate of growth, and also the increase of the bandwidth of instability. So it is important to have, it's only for the fun, to have an application. What is the effect of shear on the probability of occurrence of rogue wave, of freak wave, which are this big wave which occurs suddenly at the surface of the ocean. So there are many mechanisms which can produce this rogue wave, but the most popular is due to the modulational instability. And there is a parameter, the Benjamin Ferrer index, which measure the importance of the nonlinear four-wave interaction with respect to the typical spectral bandwidth. In fact, this Benjamin Ferrer index is a generalization of the Purcell parameter, which measures the effect of nonlinearity against the dispersion. And in the case of the NLS equation, the expression of the Benjamin Ferrer index is given by this expression, where A naught k is the wave steepness of the carrier wave, and delta k is a typical spectral bandwidth. And we have also, you see, the ratio in the square root. We have the ratio between the nonlinear coefficient and the dispersive coefficient. And this was introduced by Honorato in 2006 and in our book with Alexei Sonayev and Efim Pilinovsky. So the BFE is a convenient indicator for the prediction of rogue wave occurrence. And when this Benjamin Ferrer index increases, the probability of occurrence of rogue wave increases too. So it is interesting to look at the effect of the shear on this Benjamin Ferrer index. So here the Benjamin Ferrer index has been normalized by its value when there is no vorticity and and in deep water. So the solid line is a case when there is no shear. And when we go to infinity, we go to this value 1. And here I consider only positive value of omega, that is a co-flowing wave, and which corresponds to negative vorticity. And you can see that when you increase the shear, you increase the Benjamin Ferrer index, and so you increase the probability of occurrence of rogue wave. So for negative value of the shear, in fact, we have the opposite effect, in fact. So the probability of occurrence of rogue wave is decreased. So now I consider gravity capillary waves. So I have a new term which occurs in the dynamic boundary condition, which is here, where capital T is a surface coefficient of air-water interface, and rho W is the density of the water. So because I am working with weakly nonlinear gravity capillary waves, the slope of these waves are quite small, and we can assume that the square of this slope is small compared to 1, and so I will expand this term to third order, and we get this expression. And like for the gravity wave, I use the same procedure, that is a multiple scale method to the system of equation to third order, and I obtain in the same manner an NLS equation, but now the coefficients are more complicated due to the presence of the surface tension. So here we have the expression of the dispersive coefficient. There is a new parameter due to the surface tension, which is kappa, which is in fact the inverse of the Bond number. The Bond number is a number which measures the effect of surface tension against the effect of gravity. So now we have three parameters: mu, dispersive parameter, normalized depth, and the normalized shear, which is represented by omega bar or x, and kappa. So the nonlinear coefficient is given here. And in fact, this coefficient can be singular when these two dominators in red vanish. But this vanishing corresponds to physical phenomena that I will discuss in the next slides. This the first denominator there, when you will vanish, will correspond to what we call the Wilton ripple phenomenon. And the second denominator here will, when you will vanish, correspond to the short wave, long wave interaction. And we have to avoid these two singular value of the nonlinear coefficient. Okay, so this equation describes a resonant interaction between the two free modes traveling at the same phase velocity, but with different wave number. But this kind of situation can occur only in the minimum, at the minimum of the phase velocity, because we can find very close wave number satisfying having the same phase velocity. And it is possible then to compute the value of kappa, the corresponding value of kappa, which is given implicitly by this equation, because the frequency of the carrier wave depends now on kappa. But in the case when there is no vorticity, when the shear vanishes, we can compute easily this value of kappa, which is a classical result, which is obtained in several papers. And in infinite depths, when sigma is 1, kappa is 1/2, and it corresponds to a nonlinear resonant interaction between two free modes with wavelengths of 2.4 centimeters and 1.2 centimeters. This corresponds to a bifurcation, doubling period bifurcation. So this equation corresponds to the long wave, short wave resonance. But we can write this equation in a more elegant form, like that, where Cg is the group velocity of the carrier wave. This equation admits two solutions, but I consider only the positive solution, because I consider only wave group propagating from the left to the right. And we can observe that this expression here on the right-hand side of this equation is a phase velocity of a long gravity wave in shallow water propagating on a linear shear current of constant shear omega. And so we have a nonlinear interaction between short waves, that is gravity capillary waves, and a long gravity wave. It is clear when we have this kind of resonance that a different scaling is required, and that has been investigated by Georgievic and Redekop when there is no vorticity. But we have not developed this approach here because it's very tedious calculation. So I present now some result. This figure represents the maximum rate of growth normalized by the maximum rate of growth when the vorticity vanishes. So the solid line here and the dotted line here correspond to finite depths. So the solid line corresponds to short gravity waves influenced by surface tension, because kappa is very small, correspond to waves around 20-25 centimeters. And you can see that the combined effect of vorticity and surface tension increase significantly the rate of growth. In the case of infinite depths here, you see that the two curves are coincide, and so the effect of surface tension is very weak we have a very, very slight increase of the rate of growth in the presence of surface tension, but the effect is weak because we are working with a gravity waves influenced by surface tension. And you see that for the case, we find the result I presented previously, that is when the shear increases, the rate of growth increases too. But for the finite depth case, it's a little different. So we have an increase when the shear increases, but after a while, we can have a decrease and a restabilization. In fact, so, but in any case, if we compare when there is no vorticity, so for negative value of the shear, we have a reduction of the rate of growth of instability, and for positive value of the shear, we have an increase. So this plot corresponds to pure capillary wave. It is the rate of growth also, the normalized rate of growth as a function of the normalized wave number of the perturbation. It is P here, but because it is another paper, but it corresponds to L. And you can see also when we increase the shear, the rate of growth increases. And we have also an increase of the bandwidth of instability with the increase of the shear. Okay, so now I will present some stability diagram for gravity capillary waves. So this diagram corresponds to the case of no vorticity, and we have compared our result with those of Georgievic and Redekop in their GFM paper. The result of Georgievic and Redekop are presented by the Dutch line here, and our result corresponds to the gray and white region. The gray region corresponds to instability, and the white region corresponds to stability. So here we have five lines, 5 curves, 1, 2, 3, 4, 5. So the line 1 and 5 correspond to the vanishing of the nonlinear coefficient. And you can see, for example, for the line 1, when kappa equal to 0, that is the pure gravity waves in 2D, we have a restabilization at the critical value of mu, the dispersive parameter, of 1.363. The line 2 corresponds to the vanishing of the dispersive coefficient. That is when the second derivative of the frequency of the carrier wave vanishes, and we are in the minimum of the phase velocity. The curves 3 and 4 correspond to the resonances I have introduced previously. So note that the curve 3 presents an asymptote here at kappa equal 1/2, which correspond in fact to the value I presented previously when the depth goes to infinity in the presence of surface tension. The case, the line 4 correspond to the long wave short wave interaction here, and there is also an asymptote. We can compute the equation of this asymptote as a function of the vorticity. The line 5 also presents an asymptote, and you see that we have a large band of stability there when it goes to infinity. This was emphasized by Georgievic and Redekop. And when we have no vorticity, our result match those of Georgievic and Redekop. Now I will vary the vorticity, that is the shear, and I will look at what happened to the stability diagram. So here the shear is -2, and you see that you have a strong distortion of of the diagram of stability, we can observe that generally in shallow water, we have the stability on a large domain of kappa, even if we have a very thin tongue here of instability. So I increase now the shear minus 0.15, and you see also the motion of the boundary with respect to the case when there is no vorticity. So what is interesting, it is this, for example, I come to this case, okay? You see that we have a large zone where we have stability of a gravity capillary wave there in this domain. Okay, so thank you for your attention.
Okay, thank you very much, Dr. Kharif. It's very nice,
okay.
Very nice presentation. Okay, and now let's open questions and comments from the audiences. Do you have any questions? If you have questions, you can raise your hand by clicking the button, or just unmute your microphone and directly ask a question. Okay, any questions?
I have one actually.
Yes,
Oh.
Ari, please. Yes.
Yeah. Thanks for a nice talk. Yeah, so always a pleasure. Just have a question regarding the slides in the beginning of your talk.
Yes.
So you mentioned, that you have also vorticity if you have waves propagating over a slope. So can you elaborate on that, and maybe how can you relate the framework maybe to yes, exactly, that slide.
Is this one?
Yeah, so if you consider, yeah, exactly. So if you consider that slide, and you mentioned you get the same if you
Yes.
have waves propagating over a slope. So how this match to each other? That would be great to know.
So in fact, it is equivalent.
Yes,
It is equivalent due to the Galilean invariance.
Invariance, right?
So,
yeah.
So the only change will be the frequency of the wave, but the rate of growth will be the same.
Of course. Yeah, of course. Yes. But the question is like, how does that exactly relate?
It's on the slope. On the slope.
Mm.
Very difficult. We cannot be, because when you have a slope, the shear will change.
Of course, with the slope. Yes.
But in my presentation, the shear remain constant. It is omega. So it is possible, in fact. It is possible, in fact, because we have used that in a paper.
Yes.
Where you were the chair. Okay.
Yes.
But we use a very slow variation in order to be in the assumption of the NLS equation, and it evolves like the slow variation of the time, because it is a frequency.
I see.
So it is epsilon square T, in fact.
I see.
So it is possible, okay, and we can observe also some interesting phenomena. For example, when if we start with a breezer, when we have a breezer running on the slope, we can go to self-focusing to defocusing on the NLS equation, and we can observe dark and gray soliton on the sea. So it is interesting, because if you consider that you have a freak wave,
yes,
propagating at the sea surface and meeting a current, maybe in the same direction. For example, you can have this formation of this deep hole. Maybe it is maybe an explanation.
Yes.
I don't know.
Yes.
But it is possible. So it should be possible to derive an NLS equation with variation of omega, but it is a tedious problem, a very tedious problem.
Thank you very much. Yeah, very interesting indeed. Thank you.
But I have a question for you, Amin.
Oh, tell me.
So because Do you have investigate this problem of with an LC equation with variable bottom when you have variable bottom?
Yes, yeah. So we looked at breath evolution, obviously, on the variable depth, and indeed you can see these kind of, you know, like you have in
this is gray and black soliton.
Yes, exactly. So you have this remaining. So you start with a focusing regime, and then when you have this focusing, obviously you get these kind of holes, you know, around the freak wave, and then when you have finite depth, or I would say shallow, but finite depth, you will have this kind of troughs remaining constant, like afterwards. So that's why I found that very interesting and actually a good agreement in an experiment. So I think we should discuss anyway.
Yeah, but we have the same evolution when we vary the current only.
Exactly. Yes, in your paper
with a constant depth.
Yes. Interesting.
It's the same because we pass from the focusing to defocusing.
To defocusing. Yeah. Thank you very much, Christian. Thank you.
Okay, thank you, Amin. Any other questions? Okay, so may I ask you a question? Actually, I'm very interested in destabilization with increase of vorticity in the case of finite depths. In the case of deep water, the maximum growth rate is monotonically increasing. But in the case of finite depths, it's a maximum growth rate. It's there
is a maximum, yes, and after decrease. Yeah.
Could you explain? Can you explain physically why does it happen?
Oh yeah. So I think because if you so maybe I can take this diagram, for example, because we have the same situation. So if you are in finite depths here, you see if you draw an horizontal there, you have an unstable region, and after that you become stable. And when you approach this boundary, you have a decrease of the rate of growth, and after that a complete restabilization. That's the physical explanation of that. Maybe I have to think about.
Okay.
Yes.
Yeah. I think very much. It's very interesting. So far, I've considered only the case of deep water. So.
Yes, deep water. Yeah. Okay. Deep water were there. But okay. So I don't know. So I have to increase the dimension. The dimension there.
Okay. I think very much. Anyway, very interesting presentation. Any other questions? Okay, thank you again.
Sorry.
Yes,
Actually, it's just a suggestion, basically, because I think it would be quite interesting to see how this constant vorticity effect will play a role on like so-called spontaneous modulation stability. So let's say if you have like a regular background or condensate with noise, which generally triggers, randomly the sidebands. Obviously, the sidebands with the highest growth rate will grow quick.
Yes, it should be interesting. Yes, to have to put some noise, for example.
This is very quite interesting, especially because it's an unstable system, to see what effect of the
interesting suggestion. Maybe we can do that numerically.
Very quite interesting. Yeah. Okay. Thank you very much.
Thank you again. Thank you for the suggestion.
And nice seeing you again. It has been a while.
Bye.
Bye. Thank you.
Yeah. Thank you, Amin. Any other questions? Okay, thank you very much again, Dr. Kharif. Very nice presentation and contribution to this seminar. Thank you very much.
So I stop the share.
Okay. Okay, now, okay, nice work. Okay. So let's take a break. It's about 5 minutes, and the next lecture will start at 11 in Tokyo. Okay.
Okay, 3 o'clock. 3 o'clock.
Okay, 3 o'clock.
Okay, so
France. Okay.
okay.
Okay, let's take a break. And thank you very
Thank you.
much. Uyon, thank you very much for joining us. Uyon. Oh.
Yeah, sure. Yeah, it's a little late for me. Hi, Christian.
Hello.
Hey, good to
How
hear
are
from
you?
you.
So I don't see you. I don't see you.
Oh yeah. I'm in a bad shape, so I didn't turn on my video.
Ah, okay.
All right. Okay, I'll talk to you later then.
Mhm.
Okay. Professor Waseda, Dr. Waseda. Dr. Waseda.
Yes, yes.
Have you
Can you
met?
hear me?
Yes, yes, I can hear you.
Okay.
Have you met Dr. Kharif?
Yes, yes. Where? But I don't remember about that.
On internet.
Yes, I think several times.
Oh, really?
When is the last time? I don't know. But
Oh, it was before this pandemic.
before the pandemic, for sure. Yes.
It was in Norway, maybe, no?
Yeah, yeah. Maybe it was
it was
Christian.
for the birthday of Christian List.
Exactly. Yes, yes, yes. That's when we met. Yes. Last
Yes,
time. Yes.
It was cold. It was in November. Yes.
Yes, yes. It was cold. No, that was December. I think it was Christmas time.
This month, yeah, December. Yes, it was in December. Yeah.
I think so. Well, I don't remember. It was Scotland. Let's see. No.
No.
It was
It was in Bergen.
Bergen. Yes.
In
Yes.
in 2018.
Yes. Yes.
It was
yes.
3 years ago. 3 years ago.
Ah. Okay. Okay. Okay.
For the
Yeah.
for the 18th of Christian List. It was a kind of jubilee. Yeah.
Yes, but I just remember the Oslo one. I think it was
Yeah,
last
but
time we went all together.
it was in
Yeah.
Oslo, no? Yeah, remember?
Yeah. But it was cold, I remember, because I came from Finland, so I cannot tell. It was cold anyway, but it was really cold. So
Oh,
I
yeah.
don't know. It was, I think, yeah, definitely, yeah, November, December, something like that. Yeah. Okay. Yeah. Now I managed to switch on my camera. Oh, yeah.
Okay. Hello. Hello.
Yeah. Yeah. So was it Oslo? You said? I mean. Yes, I think so. Yeah, it was Oslo. But actually, I can check quickly. No.
No, Oslo. Yes, Oslo. It was very cold. Yes, it was a conference between Scotland and Norway.
There was something.
But it was maybe in 2017, maybe something like that.
Well, Young Guru had his 60th birthday, and I was there as well. That was in Oslo, probably. That's the one. Yes. Yeah. So because Christian Dista was from Bergen, right?
Yeah. Bergen.
Yeah.
But it was in 2018, no?